In this module, we'll discuss some problems that are relevant to this electronic schooling, and where we start with is a simple problem where we make use of what is called conduction shape factors. While conduction shape factors is a way of approximating 2D or 3D geometry into a 1D approximation, but it's often not quite useful these days or not being used that regularly because of the advent of the computers and use of more of numerical solutions. But these are quite useful when trying to do back of the envelope calculation. So where we'll begin today is that we discuss this so-called conduction shape factor and use it in an example to begin our problem solving exercise here. And as an example, if you look at the definition of a conduction shape factor, it is Q, which is the heat transfer rate, is given by is equal to some S, which is called a conduction shape factor. K is the thermal conductivity of the material, and delta T is the temperature driving forces. So in many books, for example, this is a copy paste from Encropra and DeWitt, and they have given a lot of these conduction shape factors for various configurations, and of particular use will be this case number 10 that we'll discuss, where there is a disk that sits on an infinite semi-infinite medium, and the disk is of diameter d, and which is at some temperature T1, and the semi-infinite medium is at some temperature T2, and that expression, the shape factor S that we just discussed, is given by 2D. So with that, let's look at a problem, and in this problem we have a heat source or an electronic device that is epoxied down to a semi-infinite medium, that is an aluminum block where heat is being dissipated, and the electronics chip for that matter is exposed to some hot air that is flowing on over it. So there is heat dissipation from the top side as well as from the bottom side. As we discussed previously, we will make use of this conduction shape factor in this example. This electronics component is of diameter d, and it is of some certain dimension 10 mm, and it is epoxy, and the epoxy joint resistance, the thermal resistance, it's a specific resistance, and it is given by 0.5 10 power minus 4, and please note the units, which is meter square Kelvin per watt. And so this meter square Kelvin by watt helps us to use the same epoxy joint resistance to any area, and so in this case the area being pi d square by 4, the area that is of the heat source is and this gives us the required surface area, and if we divide this area with this specific resistance, then one obtains the resistance of the epoxy joint. So let's look at the thermal resistance network for this. So the heat is being generated at point P, and the problem requests us to figure out what is the power dissipated by this component, and when you are given with, so there is a epoxy joint, and we call this, and then there is a aluminum side. This is the aluminum side. We'll first draw the network, and it goes to a sink. This is the aluminum block side, and on the other side you have some flow happening, and there is a convective resistance. So, this temperature is of interest to us, and this is given to be as some 100 degrees Celsius. Let us go back to the problem and just have a look at this. Is that the maximum allowable temperature of this component is 100 degrees Celsius, and the ambient is at 25 degrees Celsius, and we are supposed to find out, first we need to draw a network, and then we are supposed to find out what is the maximum operating power of this segment. And one important thing to notice is that it is the heat flows in both directions. That means this is a parallel circuit. Essentially I can club it as this is the aluminum side and this is my TC, and these both are at some temperature T infinity. So, assuming that TB is equal to T, this is top side. So, now one has to write the power dissipated as power dissipated by the air side plus power dissipated by the sink, that is that. So, for this we will make use of case 10 of a conduction shape factor that we just briefly talked about, and so the Q for the conduction shape factor is nothing but 2d, the diameter of that, times thermal conductivity of the aluminum block, and delta T, and this delta T is nothing but 100 degree minus, assuming that T base to be T infinity, is 25 degrees Celsius. Similarly, one can calculate, so this is known, but we need thermal resistance for our resistance network. So, we rewrite resistance for this 2D conduction as delta T divided by Q, which is nothing but 1 divided by 2D times K of aluminum. So, for the top side one can calculate based on the heat transfer coefficient, which is given to be about 25 watts per centimeter square. So, P air from the top side is nothing but H into the surface area into delta T, which is same as 75 degrees Celsius, which is 100 minus 25. And one important thing is this contact resistance that also should be accounted for. And if you look at the contact resistance, and if we write the total power now that is dissipated by this component is nothing but 25 watts into the area being about pi by 4 0.01 square times 75. This is the air's contribution plus 75 degrees Celsius divided by the, first we need to take into account the contact resistance from the epoxy or the epoxy resistance plus the 2D shape factor based analysis, and assuming thermal conductivity of aluminum to be 237, then we have our overall, this is the component from the aluminum side or the bottom side, this is the P air, and so this turns out to be 0.15 watt, while this turns out to be 88.49 watts. So, overall power dissipation is 88.6 watts. The point to notice is that the top side, if you can easily ignore for your calculation because the area of the heat source is much smaller. So when you are talking about electronics, you will find that there are so many different power components in a PCB or any system, electronic system. So it may be important to understand which side is actually dissipating more heat, and so to make an approximation that heat transfer is mostly happening on one side. In this case, for example, the heat sink side, which is the aluminum block side, is the one that is predominantly dissipating heat. So one should use the approximation that ignoring the calculation on the top side, which is the air flowing over a very small area, the heat transfer coefficient is expected to be, even if it is 100, if not 25 as we assumed here, even if it is 100, the overall contribution from the top side is very, very small. So one can easily ignore the contribution to heat dissipation from the top side as against the bottom side. So that's problem number 1. And let's look at another problem where we have, this is problem number 2. And I'm going to draw this problem. There are some PCBs mounted on this. There are about 5 of these PCBs with some components that are differently shaped. It could be anything. And there is a fan that is bringing flow into the system, and this is its exit. This is exit, and this is the inlet. Let's call this inlet is coming in at some temperature T in, and let's assume that the outflowing temperature is T out. And typically there are some planes over which these are mounted. So the flow goes through this, picks up heat from all these locations, and exits the system. So one thing is to notice is why is the inlet placed here versus, we haven't talked about what is the problem yet, but why is the inlet placed here versus why is the exit placed on the right side? Why is the inlet on the top, on the bottom down, and why is on the, so this provides, as an example, is we are talking about air cooling in a system. This provides one of the best way to balance the flow lengths. For example, this length is equal to, approximately equal to the same length. So all the flows will see equal lengths. That means distribution is important. Because we have n number of boards, one has to ensure that each board receives the right appropriate amount of airflow so that it can do its job of cooling those components. And one board may dissipate higher heat than this board. So depending on that, one may have to modulate the flow, and that is often done by putting an orifice at these inlets. So these orifices are pressure drop elements that control, if the fan is operating at a fixed speed, then these orifices provide a way to modulate the flow so that the appropriate amount of flow goes through each and every one of those boards. And the goal of this problem is that first order of business is we need to calculate what should be the minimum flow rate that goes through each of the that goes through this, the overall flow rate Q minimum that will go through, which is what we talk about is volumetric flow rate that goes through this system. That is the first question that we are interested in answering in this case. And the purpose is that we assume that the boards, each board is at 15 watts and the fan power is about 25 watts. And we have air as a cooling medium, and we know that there is a certain amount of T out, each board dissipates 20 watts and the fan dissipates about 25 watts. So the overall temperature, the T in that comes in is at 20 degrees Celsius, and assuming that it cannot exceed certain T out value, well, let us assume that the T out is to be 20 degree plus 15 degree rise gives me close to 35 degrees Celsius. The overall temperature rise is, if it is given as delta T is equal to 15 degrees Celsius, then we are asked to find the Q minimum that needs to be flown through this. So if you take this example and work it out, there are 5 cards in the system and 1 fan. So one has to, if we have to calculate the total power dissipated, then one has to calculate power total is by 5 times the power of the boards plus the fan power, and this is nothing but 125 watts, because each board dissipates 20 watts and times 5 gives us 100 watts, and the fan dissipates about 25 watts. What we make an important assumption here is that the fan is dissipating all the power that the supply to the fan ends up as a heat, is the assumption, main assumption that we are making, is that all the power supplied to the fan is expended as heating to the airflow. So assuming the 25 watts applied to the fan plus the 100 watts from all the boards is giving us 125. So in order to find out the minimum flow rate, we need to supply so that the temperature rise of 15 degree is never reached, is given by P total by the density times the temperature rise. And we know that this is 125, and assuming the density of air to be 1.1614 kilogram per meter cube times the temperature rise, which is 15 degree Celsius, will fetch us that we need to supply at least this much amount of flow, volumetric flow, to ensure that the temperature rise across the boards is less than 15 degrees Celsius. The second part of the question is such that there is a heat source that dissipates. This is part B, is that we need to now, there is a very high power dissipating heat source and it dissipates about 1 watt per centimeter square, and this is quite a large number because the flux is very high, and it needs to be placed in the system. Where do we keep this high power component within the board? Should this high power component should be placed at the entrance or close to the inlet, or should it be placed at the exit? So obviously we all know that the incoming flow is the much colder flow, so keeping a high power component close to the inlet flow is the most desirable result, so that the heat transfer can, the temperature driving forces will be large, because the colder temperature and the hottest component feasible is closer to the inlet. So, we should keep this component in the board if this is my inlet, and we should place this component that dissipates 1 watt per centimeter close to the inlet and airflow, so that heat can be dissipated much easily. For this problem, in order to calculate the surface temperature, we are supplied with what is the heat transfer coefficient that is dissipated from this component, which is mounted with the heat sink. So, the heat transfer coefficient is assumed to be 200 watts per meter square Kelvin, and that is the, so from this we, assuming the inlet temperature is T in provided is 20 degrees Celsius, we can easily estimate the surface temperature using so we are supposed to find this, and using our standard relationship, which is Q equal to HA surface area times delta T, but we do not know the surface area, but we are given a flux. So, that is equal to Q divided by surface area is nothing but H into delta T, and delta T is nothing but T surface minus T inlet. From this we can back calculate surface temperature, and this surface temperature is estimated, if you do the calculation, it is nothing but 73 degrees Celsius. So, we will move to another problem, a very simple problem, and so let us look at the slide, and that it shows that there is a RF radio frequency device, silicon device, and it has a thickness of 200 microns, that is dissipating about 0.21 watts, and its area is only very small area, which is 7 mm by 7 mm. So, the goal is to figure out, should we put molding material around this heat source whose thermal conductivity is only 0.3 watt per mm, and this molding material increases the area of dissipation from 7 mm by 7 mm to 14 mm by 14 mm. So, having this mold, will it help or hurt, is the question that we are trying to answer, and we will make use of natural convective heat transfer in doing this. So, let us look at the problem again. The problem asks for two things, is that we have a heat source, and this heat source is dissipating about 0.21 watts. It is a very small amount, small heat dissipation if we look at it from that perspective. And another is 7 mm by 7 mm, and the thickness is given as 200 micrometers. Okay, and the ambient temperature is specified as 30 degree. We ignore heat losses from, because of the 200 micron thickness, we ignore the heat losses from the side, and we assume that all the losses are happening only from the top side, and bottom is also insulated. If I draw a picture, a 2D cross section, heat transfer is happening only on the top side by natural convection, the bottom is insulated, and this is dissipating about 0.21 watts. This is the situation A, and the situation B is that now we provide a molding material around this heat source, and this molding material sits on top of this and this molding material is 14 millimeters by 14 millimeters, and the overall height is now 1.2 millimeters. The question is, having this molding material whose thermal conductivity is only 0.3 watt per meter Kelvin, will it improve the junction temperature or not? The maximum temperature of the junction should be less than or equal to 100 degrees Celsius. So, for this condition we need to find out whether the molding material will help or hurt the problem, hurt the device. So, in order to do that, first we need to calculate the junction temperature without the molding material, and then we need to calculate with the molding material. So, how to solve this problem, we will look at it in the next module.